Here's another problem. Let's imagine we have a ladder leaning against a wall. So the ladder is sitting on the floor, leaning against the wall, and let's assume there's a 60-degree angle between the bottom of the ladder and the floor. We're going to assume that this is a frictionless wall, so there is no friction in between the point of contact at the top of the ladder and the wall. We'll see why we do that in just a minute. I'll come back to that. But the floor definitely has friction, so we'll assume that there is some friction between the floor and the ladder. And let's imagine that we've got a person climbing up the ladder, and these are the numbers that go along with this problem. The mass of the ladder we'll assume is 5 kilograms. The mass of the person is 90 kilograms. We'll assume the ladder is 5 meters long and that the person is 4 meters up the ladder from the floor. What we want to do is figure out what are the forces acting on the ladder from the floor and from the wall. So let's start by drawing the forces in. What's the object in question? What's the object that is under mechanical equilibrium? It's the ladder. So we're going to draw all the forces that are acting on the ladder. So what do we have? Well, we've got the weight of the person, for example. Now I'm going to ask a couple things. For each force, I'm going to ask what the magnitude of the force is, if we know what the magnitude is. And I'm going to ask maybe three questions. What's the direction of the force? But then also, where is the force acting? Because where on the object the force acts is going to affect the torque. So we need to know where on the ladder the force is acting. So the person, the weight of the person. What's the magnitude of the weight of the person? Well, we've got a mass of 90 kilograms. We know the weight of the person will be 90 times 9.8, and that turns out to be 882 newtons. 90 kilograms times 9.8, 0 meters per second squared. So we've got the weight of the person is going to act on the ladder where the person is. We'll assume they're kind of contacting the ladder at one point. And what's the direction? The weight straight down. So straight down, here is the weight of the person. And magnitude 882. What else? Well, we've got the weight of the ladder. Well, what's the magnitude of the weight of the ladder? Well, the weight of the ladder, call it W sub L, will be 5 times 9.8, and that is 49. So the weight of the ladder is 49 newtons. Where does the weight of the ladder act? Well, what's the direction of the weight of the ladder? Straight down. Where does it act? Remember, we went over this before. The weight of an object can be assumed to act entirely at the center of the object, or the center of mass of the object. Where's the center of mass of the ladder? Well, assuming it's a relatively uniform ladder, at its center. In other words, if it's 5 meters long, 2.5 meters up from the ground. Okay, so at the center, wherever the center is, say here is the weight of the ladder. Okay, what else? Well, the floor. The floor is going to exert a normal force. The ladder is sitting on the floor, so it is going to exert a normal force. What's the magnitude of that? We don't know that yet. What's the direction? It'll be straight up. Where does it act? It acts at the point of contact between the ladder and the floor. So, at the point of contact, we'll call it F sub capital N, normal force. Okay? Then we will have a frictional force. So there's got to be some friction. If there were no friction, you probably would imagine that the ladder would just slide right out. So there's friction. What direction? We don't know what the magnitude is, okay, yet. We don't know what F sub n is, so we don't know what the maximum value of the frictional force is, let alone what the actual value at this instant is. But anyways, what's the direction? Let's think about this. The ladder would have a tendency to slide out this way, right? This way. So the friction must hold the bottom of the ladder in place. It must be pushing this way toward the wall. So the frictional force acting on the ladder is going to be in this direction. So there's the frictional force. Call it just lowercase f. F sub s, static friction. There we go. There's the frictional force. Now what about the wall? Well, the wall is going to be pushing back on the ladder, so kind of like a sideways normal force, you might say. So there's going to be a force acting on the ladder in this direction. We'll call this F sub W, force from the wall. Will there be an up or down force on the ladder up here? Well, no, not if it's frictionless. So the condition for the wall to be frictionless is basically saying that when this ladder leans against the wall, there is no up or down force. It's only perpendicular to the surface. Any up or down force and the top of the ladder would just slide on the wall. So there's no way to exert an up or down force at the top of the ladder, only perpendicular to the wall. That's the condition of it being frictionless, that the only force that can be exerted is perpendicular to the wall. Okay, there we go. Those are all of the forces. So let's start applying our conditions. We will define our x and y directions this way, as usual. X horizontal, positive towards the wall, y vertical, positive upwards. So let's write down our force equations. What do we have? F sub x. What forces act in the x direction? Well, we've got the frictional force, and that's in the positive direction, so we'll have F sub s. We've got the force from the wall, which is in the negative x direction, so we'll have minus Fw. And that's it. Everything else is vertical. So this must equal 0, which tells us the force from the wall must be equal to the frictional force, okay, in magnitude, opposite direction. Okay, what about the forces in the y direction? What do we have? Well, we've got the normal force from the floor. We've got the weight of the ladder. We've got the weight of the person. And that's it for that. So this must be equal to 0. So what do we have? We've got the normal force equals the weight of the ladder plus the weight of the person. But we already know that is 882 newtons plus 49 newtons. And we add that together, and what do we get? We get 931 newtons. There we go. So that is the normal force. Now you might think, oh, okay, well, once we have the normal force, if we know the coefficient of static friction, we can figure out the static frictional force. But keep in mind, that would give us Fs max. That's the maximum value that static friction can have. Objects don't always have the maximum value. So we'll come back to that. We won't set the value for mu s yet. We'll come back to it. Okay, so that gives us the normal force. But let's take a look at the force from the wall and Fs. Now, how might we find out what these are? Well, we still have one condition that we haven't looked at yet, and that is the torque condition. So let's set the net torque equal to 0. To do that, we have to choose an origin. Where do we want to choose our origin? Well, why don't we choose it down here at the floor? We've got two forces acting at that point. By choosing the origin down here, the R value for each of those forces would be 0, and we would have no torque for those two forces. So we'll choose our origin down here. So there's our origin. Okay, so what is our torque? Okay, well, we'll just look at each force and determine the torque for each one. And remember, torque is Rf sine theta, but then we have to consider, is it a positive or negative torque in terms of the direction? Is it tending to rotate the ladder in a clockwise direction, which would be negative, or a counterclockwise direction, which would be positive? Okay, so what's the torque due to the normal force? 0. Torque due to the frictional force? 0. What's the torque due to the weight of the ladder? Okay, so what is R for the weight of the ladder? Well, the weight of the ladder acts at the center of the ladder. The ladder has a length of 5 meters, so the distance from the origin to the point where the force is applied, 2.50 meters. Okay, what is the magnitude of the force? That's the weight of the ladder, 49 newtons. sine, what is the angle? Now, we've got to be a little bit careful here, and let's think about this. That's F, straight down. What's R? R is the vector from the origin to the point where the force is applied. And to figure out the angle, we have to put them tail to tail. So we move this up here, and the angle we want is this one here. So what is that angle? Well, if this is 60 degrees, we know that must be 30 degrees. And that must be 180 minus 30 degrees, which is 150 degrees. So sine 150 degrees. Okay, very good. Now, is that a positive or a negative torque? Well, the weight is tending to rotate the ladder down this way, which is in a clockwise or negative direction. So that will be a negative torque. Okay, there we go. Next, the weight of the person. Okay, so what is R for the weight of the person? Distance from the origin to the person. Well, we stated that was 4 meters. So I'll put it over here. 4 meters times F, that's R. What's F? F for the person is 882 newtons. Sine, what's the angle for the weight of the person? Well, the angle for the weight of the person is going to be the same as the angle for the weight of the ladder, which is 150 degrees. Okay, is that positive or negative? Again, the weight of the ladder is tending to rotate the ladder in a clockwise direction, so negative. Okay, last one, the force from the wall. What is R for the force from the wall? Well, it's going to be the entire length of the wall, which is 5 meters, times F. What's the force? Well, we don't know. So what do? Well, listen, if we want something, we have to call it something to put into our equation. So that's why we named it F sub W. We'll put that into our equation, F sub W, sine. Now, what is the angle for F sub W? In other words, what's the angle between R here and F? Now, we could move R up here, but actually it's a little bit easier. Let's take F and move it down here. So we want to find the angle between the F that's in this direction and R in this direction. In other words, we want this angle here. From the ladder to the ground on the other side, but if that's 60, that will be 180 minus 60. In other words, 120. Sine 120 degrees. Now, is that a positive or negative torque? Well, that force is going this way, tending to rotate the ladder in a counterclockwise direction. So that will be a positive torque. And that is everything. Those are all the forces. So this is the net torque, and that must equal 0. Okay, great. Well, we've got this very big equation, but the only thing in it that we don't know is F sub W. So we'll bring these terms to the other side, divide by 5 sine 120, and what do we get? We get that the force from the wall is equal to 422 newtons. There we go. And that, because that's also equal to the frictional force, we know the frictional force is 422 newtons as well. There we go. Now, I've got another question. We could certainly imagine that if there was very little friction, if this ladder, if someone put it up on an icy floor or something like that, if there wasn't enough friction, that ladder might just slide right out. How much friction do we actually have to have? In other words, what's the minimum value of mu s that's required in order to keep that ladder from sliding? Any less value and Fs max would be too small. So basically what we're saying is, what is mu sub s so that 422 newtons is Fs max? Well, let's see. So if Fs max equals 422 newtons, and we know that that is mu s times the normal force, we found the normal force was 931 newtons. So mu s is equal to 422 newtons divided by the normal force, 931 newtons, which gives us a value of 0.453. And that is the minimum value that we could have for the coefficient of static friction. We should call that mu S min. That's the minimum value that we could have for the coefficient of static friction and still have enough friction to keep that ladder in place. Very, very good. Okay, well, that is all for our mechanical equilibrium, or static equilibrium, or mechanical equilibrium. What we're going to do next time is we're going to go back to section 11 on gravitation and take a look at the gravitational force in a little more detail. I'll see you then.